Okay, we should all remember that. So this is on sections 5.1 through 5.4. We recently did 5.4. We did 5.1 a ways back, right?
Yes.
Almost about 2 weeks ago now. At least.
Yes.
So we want to make sure that we reiterate what we went over. So in 5.1 we started by talking about the idea of work and what work is. And I'm going to start with a formula to help. Okay, this is our formula for work. Force times distance times cosine of the angle between the force and distance. So for this part, it's really important that we recognize that we have, not just in this case, some random arbitrary angle, but the angle that's specifically between the actual force being applied and the force, and the displacement of the object. So let's take a look at what I want you to do for this. Give me one sec. Okay. So it's really important to recognize first that work can't be done unless you travel a certain distance, right? So if I were to push this calculator across the table a certain distance, I'm overcoming the force of friction with my force of push, if you will. For a certain distance, I can multiply those two things and tell you how much work has been done. But if I simply take this object and, I don't know, let's say I just hold it in place where it is. It's not moving, but I hold it in place. Am I doing any work? No, because no distance has been elapsed, if you will. Not time, but distance, really. If I do this, believe it or not, I'm not doing any work. It looks like I am, because you want to say you're exerting some sort of energy here, really, to hold it, right? But you're really not doing any work, because you're not applying this force over a certain distance. The distance would be 0. So work has to do with some sort of an object that's moving, right? You have to consider the fact that it's got some sort of moving parts. In that last lab that we did, the one that you guys turned in together, you recall that the object in the gym traveled a certain distance, and at the very end, when we were looking at it, we said, how would you be able to figure out how much work was done, or the force of friction, on the object as it travels through the air? Because it travels a certain distance. The distance was that arc length of the projectile itself. In 5.2, we began with kinetic energy and related it to work. How was that relationship? How did that exist? Yeah, what was the idea?
We talked about the difference between having height and kinetic energy and then moving has to do with.
Hold on. So again, how did we have a relationship between work and kinetic energy? What was that relationship?
Work equals change of kinetic energy, and kinetic energy equals half mv squared.
Yeah, this was the relationship. Again, you're talking about potential energy. It's a different thing. So the question was, how is work and kinetic energy, or how are work and kinetic energy related to one another in this case? It's the work kinetic energy theorem. Okay, the work kinetic energy theorem tells us and you should put this like a little asterisk, these little notes I tell you. It only works when we're looking at horizontal motion. Vertical motion, we have to go back to what Shaban was mentioning a moment ago, where we have potential and kinetic energy and a balance of energies, right? But here, we're looking at one-dimensional horizontal motion. One-dimensional horizontal motion.
And that's for both of these equations?
Well, for the work equation, the first one, it could be either, really. The first one, it could be not necessarily one-dimensional. It could be being pulled at an angle.
We got cosine, right? So.
Yeah, so you have the angle itself. But for this one here, right, this one below the line here, W equals delta KE, this tells me that the change in the object's kinetic energy has to go somewhere. Well, where does it go? It goes into the work done by friction. It accelerates because you're doing work on the object. So as an example, what's the kinetic energy of my iPad right now?
0.
Yeah, it's 0. Whether you know the mass or not, it's 0. Why?
Because no.
Yeah, no motion, it's not moving. Velocity is 0. If I start to push on this, right, and I get it to go faster and faster and faster, I'm increasing its kinetic energy until I let go at the end there and it stopped, right? Why did it stop?
You stop pushing.
I stopped pushing, and what stopped it from moving? Friction. So initially, for this example, I did work on the object by pushing it. Then as soon as I let go, friction did work on the object by slowing it down. So all the energy that I gave the iPad, so it had 0 joules here, maybe it had like 20 joules here, and then at the end it stopped again, so it's back to 0 joules. So I gave it 20 joules of energy by applying a force over a certain distance. I did work on the object. and as a result I changed its kinetic energy. But then as soon as I removed that force, friction changed its kinetic energy and reduced its kinetic energy to a level of 0 at the end. The concept is this. If we're given some facet or some knowledge about velocity and mass, and we can see that there's a change in that velocity, we can easily calculate the work done simply by doing KEF minus KEI. Okay, so this is the formula you're given, but this is what you should remember. Final minus initial is what delta is, right? KE final minus KE initial. And as Leckham told us, KE is 1/2 mv squared. And this is final minus initial. Okay, that's really the formula you're going to utilize, that one at the bottom there. The one at the bottom is the one that we're going to really utilize. Now, if you wanted to find out how far the object traveled, and I told you what the applied force was, you could replace work with F times D. This is if you were actually trying to figure out the force and not the work, maybe. But if you're trying to figure out how much work is done on the object, you could utilize this formula here, plug in the numbers you know here, and you'll get how much work was done on the object. But what if you're trying to find out how far the object slid, right? Like that extra credit I reminded you about last night in that email? If you're doing that extra credit, this is your formula right here. This is it. Okay, and in the extra credit, what I told you was that you wanted to figure out the mu value. Well, F is the force of friction in this case. You can replace that with mu Fn, and we did that in one of our examples, one of our notes. One of our examples in our notes, we did that together. And you had to determine the distance traveled. In the extra credit, I want you to figure out the mu value. So go back to the example in 5.2 and look at it if it helps. But this was the governing formula. Depending upon what this force is, I really can't go further yet. If I know that it's friction that's applying the force to slow it down, I could replace F with mu Fn, because that's what friction is. If I know it's some applied force, and the applied force is accelerating or causing it to increase its velocity or increase its kinetic energy, and I give you that force, and I say, what is the distance traveled while that force is being applied? Or for how long does that force, or is that force applied? You could just divide by F and solve for D, assuming that theta is some value given, or maybe it's just 0. When is theta 0? Theta is 0 when you're pushing what? Anybody know? When is theta 0 in this case?
When you're pushing in the same direction as before, when you push the same as...
It's motion. When your force is applied in the same direction as motion, theta is 0. That's usually some sort of a horizontal push or pull. Now, friction, what is the angle always? Anybody? What is the angle always? 180. Okay, because remember, if the object is moving this way, friction is clearly acting this way. What's the angle between my arms? 180 degrees. Okay? So for friction, theta is always going to be 180. Let's see. So clearly work is a function of the amount of force applied and the distance traveled. The amount of force applied and the distance that force is applied for, or distance traveled. That's what work is a function of. What is kinetic energy a function of? Kinetic energy is a function of two things. What are they? The formula is right there for kinetic energy. What is it a function of?
Force and distance.
No, kinetic energy. That's work. Work is force and distance. Kinetic energy is a function of what?
Mass and velocity.
Mass and velocity. If you have more mass, you have more kinetic energy. If you have more velocity, you have more kinetic energy. They are directly related. You were about to say proportional, which is fine for mass. Mass is proportional to KE, but velocity, it's the square of velocity that's proportional to KE. But directly related works for both. Okay? If you double the mass, you double the kinetic energy. If you double the velocity, though, you quadruple the kinetic energy. Why is that?
This square.
Yeah. If you double V, eventually you're going to have to square that doubling factor, which really makes it a factor of 4. If you triple the velocity, it goes up by a factor of 9. It's squared, right? Look at the term. If you quadruple, the velocity goes up by a factor of 16. Does everybody see what I'm saying? I'm trying to point as I do this, so it might be helpful to look up, right? So as I change the amount of velocity, my kinetic energy changes by the square of the change in velocity. So if you change the velocity from 2 to 10, forget units, 2 to 10 for now, that's a factor of 5, right? Increase to go from 2 to 10, it's a factor of 5. So you're quintupling, or whatever, multiplying the velocity by 5. If you change the velocity by a factor of 5, the kinetic energy goes up by 25, meaning 25 times what it was. Okay? As opposed to mass, if you double the mass, it doubles the kinetic energy. If you triple the mass, it triples the kinetic energy. What if I do this? What if I triple the mass and double the velocity? What happens as an overall result? Let's say for kinetic energy, right? Let's say I triple the mass and double the velocity. That's what it looks like, right? That's what that means, to triple the mass and double the velocity, what I'm writing here. So what overall effect would that have on the normal kinetic energy? Remember, normal kinetic energy is 1/2 mv squared. So how much bigger is this than 1/2 mv squared? Siobhan?
12.
What is it?
12.
Yeah, very good, Siobhan. She recognized this because look, this is 1/2. This 3 that's in front here, I'm going to leave out here. This v is going to be squared. I'm going to put that out here. But this 2 here has to be squared. That comes out as a 4. So that's really what it looks like. Think about this for a second. The triple mass, that's a 3. The double the velocity, well, double velocity, you have to square the 2 because it's inside the parentheses. It's 4 times as much. If the velocity increase makes it 4 times more, but the mass increase makes it 3 times more, it's in the end 12 times bigger than what it was. So I could say that the kinetic energy went up by a factor of 12 in this scenario. A factor of 12 in this scenario. Does that make sense what I'm saying there? Think about your direct and indirect variation. Okay, what is directly and what is indirectly related? We began section 5.3 by talking about the types of energy. We had kinetic energy and we had potential energy. What's the difference? We already talked about kinetic, obviously, but what's the whole idea with the potential?
Potential is how much possible energy it has, so if you have it off, then it has the amount of energy it would take to go all the way down to the ground.
Yeah, so Nick gave us the example, of gravitational potential energy, depending on where it is vertically. What other kind of potential energy is there?
Physical height. It's energy of height.
Elastic.
Elastic. Listen to what he says. He just said.
Spring. Oh.
Elastic or a spring. Remember, you can store energy in a spring as well. So you have potential energy that's elastic or spring energy, and then you have gravitational potential energy, which is based on its height. Kinetic is based on its velocity. Yeah, if you could. It doesn't have to be neat, John, just a big pile sign. So let's talk about that and the idea of conservation. Okay, that's what 5.3 kind of brought us into. So let's go ahead and discuss. 5.2. 5.1 was work. 5.2 was work kinetic energy theorem and what is kinetic energy. 5.3, we began the concept, well 5.2 actually, I guess we did still talk about potential energy in 5.2, but then in 5.3 we talked about all of them together, potential and kinetic energy all in one problem, how it's related. So let's look at an example to explain this, right? Pendulum, swinging back and forth. We did this in class, we talked about it real quick.
Totally be on the test. It's totally be.
Oh, it'd definitely be on the test, the pendulum. A pendulum, or the idea of a model of this, right? Like remember in the lab that you guys started, that FET lab the other day, the skateboarder? The skateboarder is the exact same thing as a pendulum. They're absolutely identical. The pendulum does this. Well, the skateboarder does this. If friction is off for the skateboarder, friction is off for the pendulum. It's the same problem. If there's air resistance, then there's friction involved. But again, the concept is the same. It's a model. So, what kind of energy does it have at the top there? It's got potential energy. And once it's moving, it reaches the bottom, and we're going to call the bottom ground level. Remember I do this? We're going to call this ground level. And whenever you want ground level, you write P equals 0. That means ground level. Okay, you saw that in your lab, in your FET lab. It said P equals 0 there. This is the potential energy reference line. So when this pendulum is at the bottom of its motion, it's all kinetic energy. So it's a constant transfer of potential to kinetic, back to potential, back to kinetic, and back and forth, except when? Except when? Yeah, when this object, this pendulum or the skateboarder was halfway up the ramp, maybe like here at this point, right there, it's both potential and kinetic energy. Because the pendulum has some height still, so it has potential, and it also has velocity, so it has kinetic as well. Okay, both kinetic and potential energy there. Yeah?
So like, depending on the question, you would have to say how much kinetic or potential energy does it have in the middle of its pathway, or would you usually the question says?
So let's say that you have 10 joules of potential energy in the beginning, okay? And then I tell you that you lose 6 joules of potential energy. So as a result, where do those 6 joules go? They go into kinetic, so you would know how much kinetic you have. But there's always that balance where you're going to use MEI equals MEF. Okay, that's where it's going to come back to. So let's see what Shabana's talking about there, because that's what we're going to do next anyway. We're going to look at our formula for conservation, which tells us this. Okay, that's what our formula tells us. It tells us that the amount of energy before equals the amount of energy after. And before and after just means at one point in time, and then at another point in time. So this pendulum in the beginning only had potential energy, but let's make it a little more interesting. Let's make it a little more fun. Okay? Let's say that this pendulum is attached to a spring. Oh, that's a whole lot of fun. Okay? And let's say that the pendulum is compressing the spring until you pull a pin and the spring shoots the pendulum out. Right? It launches the pendulum, and after the spring launches, the spring kind of moves out of the way. Let's say there's a mechanism to remove the spring so it doesn't come back up and hit it. So if there's a spring holding that pendulum in place, okay, it's got some energy in the spring. It's got some energy because it's a certain height above ground level right here. Then it's launched, if you will. I'll use the word launched, even though it's not like launched up. But it is launched. It starts to accelerate toward the bottom. It's going to come back up to some height, and then it's going to come back down. So the way we would analyze this kind of a problem is we would say the following. We would say, let me just move this up. Oh, I can't
Can we
move it
go
up.
further because you're putting more force?
Yeah, we'll get there. We have in the beginning potential energy stored in the spring because the spring is being compressed. We've got potential energy due to the height of the object in the beginning. And then at the very end of the path, we'll call this initial, by the way, and we'll call this final at the bottom here. Initial is where it started, final, we're going to call the bottom final. At the end of the path, it's got kinetic energy. Now, for a problem like this, you're giving the system more energy from the spring. The spring is kind of like saying, I'm going to give you a ton of energy and launch off. But on the other side of the pendulum, is it going to hit? Is there another spring over there?
No.
So that's what Shaban was alluding to. Instead of this object attaining the same height over and over again, it's going to actually get a little bit further up in its path because the spring gave it that little jump start. So what's going to happen is this object is, let's say this angle, by the way, the way you measure, we're going to do this later in the year, but the way you measure starting points for this is angular displacement. So let's say this angle is 45 degrees. You start from 45 degrees and the spring launches it. All I know is this. All I know is this angle is going to be something greater than 45. Let's for now call it 60 degrees. But it will definitely get up to a higher elevation than it started. Again, why? Because the spring energy in the beginning got put into the object, which increased its velocity, which gave it more kinetic energy than you'd expect. So if you want to find the kinetic energy at the bottom, you're going to set it equal like we did here. If there was no spring, what would I do? Yeah, but mathematically. If there were no spring involved in this problem, what would be the only difference? Okay, that's all. Cover that up. Cover up PES, and that's the problem now suddenly. You can find the kinetic at the bottom equals the potential at the top. If you know the velocity or the displacement or whichever one, you can figure out one of the other. Okay, this is what you've been doing with your homework problems. Same problems you've been doing over and over again. If you've been doing well with the homework and you have no problems, and it seems that way because I haven't gotten any questions about homework, but if you've been doing all right with it, you should be fine with mathematical problems here. But tonight, obviously, what are you going to practice? Problem sets. Okay? Yeah.
I have a question, but it kind of goes off the pendulum. But it's about, okay.
It's a C-Day, come on.
There's a homework question about the big runner jumping and it's finding the central height at the top. well, how would you find the central height or the central mass?
Okay, so objects are measured from center to center. So the book is just referring to the center of the mass as where you started from. So if I start right here and I jump up and I freeze frame, you measure the distance from where this was initially to where it is up there. That's all that means. So it's pretty much saying find the change in elevation.
Okay.
Okay? The height of the center mass. So if you start at the ground and you end up here, it's asking for the Y value in that case.
What's PES?
Potential energy in a spring.
Oh.
Remember what's the formula for that? Anyone remember? You're right, Chris. 1/2 kx squared. The first one you had was good. Okay, this is what we would have for this problem. You have spring energy in the beginning. You've got height energy, potential energy of height in the beginning. You've got kinetic energy at the end. We started at this height. We're trying to figure out, let's say, the velocity of the object at the bottom. You want to find the velocity at the bottom. What should I do to find the velocity? How do I solve for the velocity at the bottom of the pendulum? And start by multiplying by 2. Very good. And then? Yeah. Multiply by 2 to start. The 2 and the 1/2 cancel. Now this 2 has to get distributed to both, so it cancels with the 1/2 kx squared, the 1/2 from the kx squared portion, but it still gets applied to a 2 mgy here. And then as Ant mentioned, we're going to then divide by mass. And if I want to get v by itself, I'll also take the square root. That gets rid of the square on the right-hand side. So that would be the velocity of this object at the bottom of the ramp if there were a spring that launched it to start. So when you guys take the test on Thursday, you need to simply analyze the instance that I'm referring to. So if it starts on a ledge, on a compressed spring, a height above the ground, it's the exact same problem as this. This started in a spring compressed at a height above what we call ground level. And if you want to find the impact velocity, if after it's launched off the cliff and it lands on the ground, that's what we're determining right now. This solution is the exact same solution if I were launching an object from a cliff on a spring. It's the exact same answer. It does not change. So modeling is very important here, right? We take the idea that we have to look at the problem, draw some sort of a diagram, identify what kind of energy it has at different instances in time. So if I have a spring on a cliff, it's the exact same thing. It's got potential in the spring, potential and height to start. When it hits the ground, it's only got kinetic energy. It's the exact same problem. Nick?
There's mechanical energy, PE spring plus P.
Again, it depends on the problem every time.
For this one.
For this one, the initial energy is PE spring plus PE. The final energy is KE. It changes every problem, Nick. There's no answer to that. You can't say mechanical energy is this or that. It changes based on the context. Okay.
Why does M doesn't cancel there, or do you cancel?
Because the kx squared has no m in it, right? How could you cancel m? Remember, you have a binomial on the top. You have a monomial on the bottom. To cancel what's in the monomial, it has to be in all terms. There's no m over here, okay? Only when you have an m in all the terms can you drop it off. The k throws it off, the kx squared. So again, depending upon the problem you're given, it will change. So you have to learn to adapt. That's the hardest part about physics. This is not cookie cutter like you learn, with basic science classes. So I'll try to minimize the work on power, but let's look at another example. Let's say that an object starts on the ground, okay? And it starts loaded in a spring. So let's put the ground over here. Let's put a spring coming off the ground at maybe an angle. Put the object here. And let's say that this object is launched and is going to land up on a cliff over here. What kind of energy does it have to start? Again, it's not moving. It's stored in the spring. It's not moving to start. Remember, these problems, whenever it's stored in a spring, it's not moving. Is that clear? It's not moving.
Potential energy velocity.
Potential, say again?
Potential energy velocity.
Elastic, okay. I thought you said velocity, and I was like, oh no. No velocity, good. Elastic, that works. So that's what the energy in the that's it. That's all it has. We're assuming it's on the ground. I know that the spring has some height to it, really, right? but let's assume that the spring is compressed so that it's on the ground at this point. So that's our energy in the spring. Well, we need to know how far the spring is compressed. That's X, remember? K is the spring stiffness, the strength of the spring. That'll go in our formula. Now, let's say that when it reaches the top, it's still moving. Okay? It reaches its max height, and it's falling on the way down. It's still falling on the way down, and it hits that cliff right there. And our goal, let's say I give you the height, and our goal is to find the velocity when it hits at the top. What kind of energy does it have at the top? It's still moving. Yes. This is the hardest part of these problems. Literally just identify. In the beginning, it's only spring energy. It reaches a certain height, it still has some velocity, thus it has potential and kinetic at the top. Now, if we want to figure out what that amount of velocity is at the top, we could solve for V again. It would be a little bit different because now we have, what's the energy before? Remember, this is our formula to start. Nick, this is where I'm getting to your point here. This is always the formula to start, but now what's the energy initially? What kind of energy does it start with? Only spring energy now. It does not have potential energy of height anymore, like the pendulum did. But at the end now, it's not just kinetic energy anymore, right? It's also potential energy at the end, because it has some height. I'm going to replace these with formulas that I know. I know a spring is this. I know kinetic energy is this. And I know potential energy is this. So that's what I start by writing always. Just write your formulas right in. Please, write them in. Now, it doesn't matter what you're solving for. Let's say I told you that the velocity at the top of the cliff is 5 meters per second. And the mass is 2. And the spring constant is 7. And the displacement of the spring, or the stretch of the spring, is 2 centimeters. Convert that to meters. 0.2 meters. And you want to find out the height of the cliff. Now you're solving for y. Or maybe you want to find out the velocity when it gets to the top of the cliff. And I give you the y. Now you're solving for v. Or maybe I say, how far should the spring be compressed for this to work? And I tell you everything about the height and the velocity. Now what are you solving for? X. The spring's compression. If I ask you to find the spring stiffness, it's K. Okay, or the spring constant, it's K. So what I'm getting at is this. Every problem is different based on the context and based on what you're solving for and what you're given. So it's extremely important that you list all your givens, as we always do. You need to know units. If you see units of newtons per meter, that's K. K's units are newtons per meter. I know that. You should know that as well. The units for velocity are meters per second. If you see a unit of meters, it could be height or it could be the compression of the spring. It could both be given in meters. So then you have to read the context of the problem. It might say the cliff height is 12 meters. Well, that's y then. Or it might say the spring is compressed 3 centimeters. 0.3 is going to, or 0.03 rather, is going to be your x value. Remember that things need to be in meters. Some of the times with a spring is very small, so I'm not going to tell you like it's compressed 2 meters. That wouldn't make much sense. Unless it's like the springs at the end of like, you ever see a train at the end of the line, there's like a big cushion? Ever been to the end of a train line? There's like always like this cushion there. It's a spring really. It's a spring that could be compressed like 3 or 4 meters before the train would crash into the wall. It absorbs the energy at the end of it there.
Do we have to convert it into meters? Like if you give
Yeah, so that's what I'm saying. So everything should be in meters when you're talking about distance. Everything should be in kilograms for mass.
Is that when you divide it by 1,000 or multiply by?
To get from centimeters to meters, you divide. Because think about it. A centimeter is much smaller than a meter. So it's going to be a fraction of a meter. Okay, that's how I remember it always. So listen real quick. Tomorrow, the other class, I'm going to be also recording and reviewing with them. So I'm going to have a little more time in their class to record and review. So feel free tomorrow night to watch their video. Okay? But tonight, problem sets. I think I put due by noon, right? Did I put a time? I think I put due by noon tomorrow. So that means at noon they need to be submitted by then. If you do a hard copy, give me the hard copy. Okay, but make yourself a scan of it first. But give me the hard copy. Please don't scan the hard copy and submit that to Dropbox. Give me the hard copy if you have it at some point, but copy it for yourself.
K is always constant, right?
K is a constant. Yeah, it's the spring constant.
constant, yeah.
Always. It's the strength of the spring.
Yeah.